All right, good morning, pre-calculus. Today we're going to do 11.5a, which is the area problem. This is what a lot of calculus deals with. So we're going to take you back to chapter 8, section 3, which was series, arithmetic and geometric series, specifically the infinite geometric series. So the formula for the infinite geometric series was the first term plus the first term times the common ratio plus the first term times the common ratio squared. And that common ratio was just when you took the second term divided by the first term, the third term divided by the second term, and so on. So here we get the sum equals from equals 1 to infinity equals the first term times r to the I minus 1 power. Okay, and then we can rewrite it as the first term divided by 1 minus r as long as the absolute value of that common ratio is less than 1. So using limit notation, we can rewrite that using our limits. Okay? And you'll see that it changes from the summation notation to just the limit notation. So that becomes the sum, so limit as x approaches infinity, of our first term times 1 minus r to the n over 1 minus r, which equals our first term divided by 1 minus r. So knowing that geometric series and the limit notation, we can actually rewrite the sums that we're going to work with here in the future using this. Okay, so we actually have some formulas we're going to look at. So the first one is sum from I equals 1 to n of a constant. So some number. That's just going to be the constant times n. For the second one, we're going to look at the sum of I equals 1 to n for I. Okay, that's going to equal n times n plus 1 over 2. We can also rewrite that as n squared plus n over 2. So all I did was I went on ahead and distributed that n through. Okay, so the same thing for I squared. We're going to have n times n plus 1 times 2n plus 1 all over 6. And I'm going to go on ahead and rewrite that one also because we're going to use it kind of frequently. So I like to give you guys this version of it also, which is just the simplified version of it. Okay, so it's the one where it's already distributed. And then the next one we're going to look at is the sum from I equals 1 to n for I to the third power. So that's n squared times the quantity n plus 1 squared, all divided by 4. And we can rewrite that one also as n to the fourth plus 2n to the third plus n squared, all divided by 4. So these last two have to do with adding or subtracting summation formulas and multiplying a summation formula times a constant. So anytime we have a summation formula that has two of these added together or subtracted, we can break it up into their individual summation formulas. Okay, so if this one was a C, we would put, okay, well, the sum of the C, and then for the next one, we would put the sum of the I. Okay? So we can break them into two different summation formulas. And this one just says that if there is a constant, okay, times your A1, okay, or your formula, then you can pull that constant out and it can be multiplied times that summation after you've done the summation. So let's go on ahead and take a look at some examples here. So I'm going to warn you to write small on several of these because they're going to take some room up. This one doesn't take much room up, but this one right here and the next one are going to take some room. So you're going to want to write small, okay, or maybe write out in the margins a little bit. Okay, so this one right here, it just says the sum from I equals 1 to 200 for I. Well, looking up here, we know that our formula for the sum from I equals 1 to n for I is n times n plus 1 over 2, or n squared plus n. So I'm just going to replace that with n squared plus n over 2. And now I'm going to replace those n's with that 200. So it's going to become 200 squared times 200 all over 2. I'm going to plug that into my calculator and I get 20,100. So in other words, if I if I add up the first 200 terms of this this formula, I'm going to get 20,100 as my total. So let's go on ahead and look at the next one. And once again, this one's going to be long, so let's write it kind of small. So this says evaluate the sum for n equals 10, 100, 1,000, and 10,000. So that's going to change this number up here. But this right here says I plus 2 over n squared. Well, there is nothing up here that says I plus 2 over n squared. So we need to get it in a way that we can read it, okay, and the way that we can work with it. So I know that I can do I plus a constant, but what should I do with this n squared? Well, that is going to be using this number 6 right here where I can pull a constant out. So the first thing I'm going to do here is I'm going to pull my constant out, so 1 over n squared, and then I'm left with the sum from I equals 1 to n of I plus 2. But once again, I have an I plus a 2. So using this information right here, this formula and property, I know that I can break those into two separate summations. So now I'm going to break that up into 1 over n squared. Okay, this summation goes away, and the I is just n squared plus n over 2 plus, and now it's going to be the Cn. So that's going to be 2n. Okay, well, I have some fractions in here, so I want to get common denominators. So if that's a 1, I need to multiply it by 2, and whatever I do to the bottom, I have to do to the top. Okay. So now I'm going to have 1 over n squared, and then I'm just going to leave this n squared plus n as it is, but then I have a plus 4n, and now all of that is over 2. Okay, so I got a common denominator, and I added them. Well, I have some like terms here, so let's go ahead and do that. So 1 over n squared times n squared plus 5n all over 2. All right, now I'm ready to put this in. So now I'm going to multiply this 1 over n squared through this. So I have n squared plus 5n over 2n squared. Okay. But I have an n in common in all of these, so this can go away. And I'm left with n plus 5 over 2. And if you're uncomfortable doing that, then just pull an n out. So I'm going to come over here and show you guys that. So it would be n times n plus 5 all over 2 times n, because that's n squared, and then one of those would cancel. Okay. So now I have my final summation formula. Now I just need to figure out what it is at each of these values, 10, 100, 1,000, and 10,000. So I can just do an X and a Y, and I can just plug those values right into my calculator. Okay, so 10 plus 5 is 15. Oh, yeah, 15 divided by 20. Okay, and I would get 0.75. Okay, 100, 1,000, or 10,000. Okay, the other way I can do this is I can actually plug it into my y equals. So here it is. So x plus 5 divided by 2x. Make sure you put that in parentheses so it doesn't do x plus 5 divided by 2 and then multiply everything by x. Okay, and I already did my 10. Okay, so I'm going to go to my table and I'm going to start at 100 and I'm going to go in increments of 100. And because I don't want to be scrolling through this forever. So my 100 is 0.525. So now I could start scrolling and get to 1,000 pretty quickly. So that's going to be 0.5025. But then to get to 10,000, it's going to take me a little while. So for me, it's just easier to go, okay, well, let's just start at 10,000 and go in increments of 100. Okay, nope, there's my graph. All right, so 10,000 would be 0.50025. Remember, you can also, store your Y1 and then you can plug it right in, okay, if you remember how to do that, or just plug the numbers in, either way. Okay, so now I know, looking at this, that my limit as n approaches infinity, because it was getting bigger and bigger and bigger, for this n plus 5 over 2n is, well, let's take a look. It started at 0.75, then it went to 0.525. It got closer to a half, and I bet it will just keep getting closer to a half. Okay, so that's going to equal 1/2. Okay, so we found that limit as it approaches infinity. All right, let's go ahead and take a look at the next page if I can find it. Here it is. All right, sorry, my desk is a mess right now because I'm all over the place. All right, so we're going to do another one. Remember, this one's going to take up some room too. I should have left you guys more space, but I didn't. I apologize. So it says find the limit of s sub n as n approaches infinity. Okay, so here we have this summation formula, and it says expand and factor out the constant, and then we're going to write it as 3 summations. So the very first thing I'm going to do is expand this. So I see this 1 plus I over n squared. I'm going to go on ahead. I'm going to come out here in the margin. Let's see. Let me raise this camera a little bit so you guys can see what I'm writing. Okay, so I'm just going to do 1 plus I over n squared, which means 1 plus times 1 plus I over n. 1 times 1 is 1, plus I over n, plus I over n, plus I squared over n squared. So that's going to give me 1 plus 2I over n plus I squared over n squared. Well, now I'm going to go on ahead and get a common denominator. Okay, we don't want to leave these separated just because it's going to be easier in the long run if we don't. Okay, so let's see. N squared. That's what I need to do. So I need to multiply that times an n and that times an n. And I need to multiply this by an n squared and an n squared. All right, so now I wind up with n squared over n squared plus 2in over n squared plus I squared over n squared. Okay, what this allows me to do is pull out an n squared. I already have a 1 over n here, so if I pull out an n squared, that's going to be 1 over n times n, 1 over n squared, okay, which is going to be 1 over n to the third. All right, so now we're going to write these as our summations. Okay, so we've gotten rid of that. Now we have individual summations that we can write. So now we're going to have the summation from I equals 1 to n of this first one, n squared, plus the summation from I equals 1 to n of 2in. Okay? Remember, n is just a number here. Right? It's like a constant. Okay? Plus, and then we're going to have the summation I equals 1 to n for I squared. Okay? So now that we've gotten that, now we're going to go on ahead and rewrite these using the summation formulas that we talked about on this previous page here. Okay. All right, so we have, let's see, that goes over there. So we have 1 over n to the third times, okay, n squared is a constant, so that's going to be n times n squared plus, okay, 2in, so that's going to be 2 times n squared plus n all over 2. And then, and I'm not going to cancel those 2's yet, and you'll see why. Okay, and then we're going to have plus the I squared, and that is 2n to the third plus 3n squared plus n all over 6. Okay, once again, we need a common denominator. We're not doing anything without common denominators here. So my common denominator is 6, so this whole thing needs to be multiplied by 3 and 3, and this needs to be multiplied by 6 and 6. So that 1 over n to the third is still out there. Okay, I'll deal with it in just a minute. Okay, so now I have 6n to the third plus, that's going to be 6n squared plus 6n. I forgot this in here. Uh-oh. It's a good thing I checked that. So that's going to be 6n to the third. Did everyone see that, what I did? So this is 2in. So 2in itself is this, but then I had another n I have to multiply by. Okay, so that's going to be 6n to the third plus 6n squared, because 2n times, or 6n times n, plus, and then this one just stays the same, 2n to the third plus 3n squared plus n. And it's really important that you get these right, because you're going to see why in just a second. All right, so now I'm going to distribute this into the third. And I'm going to combine my like terms. So 6 plus 6 is 12, 13, 14. So I have 14n to the third over 6n to the third plus, let's see, 6, 7, 8, 9n squared plus n. All right, so now I'm going to do my limit as n approaches infinity. And this is the one where we look at those asymptotes. So these are the same, which means it's this coefficient over this coefficient. That's why these numbers are so important. If we get them wrong, then this coefficient's going to be wrong. So in other words, our limit as n approaches infinity is 14 over 6, which reduces to 7 over 3. Okay. So it's really important that you pay attention to this stuff. And I tell you, every time I do this problem as an example, I forget that n. Okay, so really pay attention to what you're writing down here, because if you're like me, you're going to forget something like that, and it's going to make a big mistake here. Okay. All right, so let's talk about how this relates to area. So the area problem is actually found by creating rectangles. So we are going to discuss the area under this curve by two vertical lines. We'll just say from here to here, and the x-axis. Okay, so we just want to know this area right in here. So what we're going to do, we'll say, oh, let's break this up into, I don't know, 1, 2, 3, 4 equal rectangles. So we can find the rectangles, the areas of all of these rectangles, right? Right, and our rectangles have to come out. They have to be complete rectangles. So we can find the areas of all of those rectangles, and we could add them up. Okay, so that's one thing that we could do. But you notice that there's a lot of overage here. Okay. So if we want, we could make more than 4 rectangles. We could make this into 8 rectangles. And 8 rectangles, there's going to be a lot less overage. Okay. So that means that that we are going to be able to get a more accurate reading. So really what we're saying is, as we make more rectangles, okay, our n values from over here from these summations is getting closer and closer to infinity. So the smaller the rectangles, the more rectangles there are, the closer to infinity the number of rectangles, the absolute better or closer to the real area you're going to get. Okay, so that is how you find area under the curve and bounded by, usually it's some vertical lines in the x-axis. Okay, so let's actually take a look at one of these problems. So for this problem here, we're going to use 5 rectangles to approximate the area under the curve. The curve function is 6 minus x squared. We're going to stop at the x-axis, and our vertical lines are here at 2 and at 0. Okay, so we're going to need 5 rectangles between 2 and 0. So that's going to break this into, let's see, 2. So that will be here. Okay, that's why I have these numbers here. Let's see if I can draw a straight line. I try to usually have this done beforehand. All right, so we're going to have these 5 rectangles here. Okay? So this one, this one, this one, this one, and this one up to 2. Okay? So we're not going to want to go past this. Okay? But remember, these are rectangles, so it's going to be a little bit off, and we only have 5 of them, so it's going to be a little bit off. All right, so the 5 intervals that we're looking at are 0, so 0 to 2/5. That's our first rectangle, okay, because this is 2 out of 5. Okay. So it's the number 2. So how many x's we have in our interval divided by 5 rectangles. Okay. And then it's going to be 2/5 to 4/5. And then it's going to be 4/5 to 6/5. Then it's going to be 6/5 to 8/5. Then it's going to be 8/5 to 10/5, which is 2. Okay. So those are our 5 intervals, are our 5 rectangles. The width of each rectangle is 2/5. Okay. So if we take 0.4, right, and say, okay, well, 0.4 is 2/5 of 2 as a whole. Okay, so what I said, remember, is all we're doing is we're taking this, okay, so we're taking b minus a, and we're dividing that by 2. Or sorry, we're dividing that by the number of triangles, which in this case is 5. Okay, so 2 minus 0 is 2 divided by 5. Okay, here it's going to be 4 divided by 5. Okay, so we're going to just keep doing that. All right, let's see where I'm at. So the height of each rectangle is going to be 2i divided by 5. Okay, so really what that is 2 times the function, or the part here, the x part of the function, divided by 5. Okay, it's our width at this particular x point. Okay, so that's why we're calling it I. So that would be 2/5, 4/5. Okay, so you notice it's going to be there. Okay, so where I corresponds with 1, 2, 3, 4, 5. So that's corresponding with those right sides of that triangle here. Okay, or those rectangles. I don't know why I'm calling them triangles. All right, so now let's go ahead and take a look at the sum of the rectangles and how we actually work this problem. Okay, so now we're going to have a sum from I equals 1 to 5 of the function times 2i, the function where it's 2i over 5, and then 2 over 5. Now this right here is an important piece. What that means is in our function, anywhere we see an x, we're putting 2i over 5. Okay, that is function notation. That's all that is. Okay, so now I'm going to go on ahead and rewrite this using that function notation. So I have the sum from I equals 1 to 5 of, now this is going to be 6 minus 2i over 5 squared, okay, because it's x squared, okay, and then that's going to be times 2 over 5. Okay. All right, so the next thing I can do is I have a constant here, so I'm going to pull that constant out. Okay, so I have 2 over 5 as my constant. I always forget my do-wop. I equals 1 to the 5th, 1 to 5. Okay, so we're going from one rectangle to 5 rectangles. Okay, now I'm going to do this. 6 minus 2i squared is 4i squared over 25. Okay. So now I'm going to go on ahead and just keep working my magic here. Okay. So I'm going to break this up into 2 separate pieces. So now that's going to be 2 over 5. I equals 1 to 5. Okay. And now that's going to be 1 to 5 of the 6 plus, oh, minus, see, minus here. So we're going to do minus the sum of I equals 1 to 5 of 4i squared over 25. Okay, so let's go on ahead and rewrite this. So now I'm going to rewrite this using my handy dandy summation formulas here. Okay, so it's going to be 2/5 times that 6 just becomes 6 times my n. And in this case, I have a value for n. It's not just n. My n is 5. Okay, minus, okay, now this is going to become 4 over 25 times my I squared stuff. And looking back at this, my I squared is this one, 2n to the third plus 3n squared plus n over 6. Okay, so I'm going to rewrite that. So 2n to the third plus 3n squared plus n over 6. Okay. All right, and now I'm going to go on ahead and I know what my n value is. Once again, it's 5, so I can plug that in. So I get 2/5 times 30 minus, and if I plug 5 into each of these, and then I'm going to get 44 over 5. And now I can just do the math. So I can do 2/5. I'm just going to get my calculator out, and I'm going to do 2 divided by 5 equals times, and I'm going to do parentheses 30 minus 44 divided by 5 and close my parentheses. Now, when I do this, it's going to do the multiplication after it does what's in the parentheses, and 44 divided by 5 before subtracting because of order of operations. Okay, so I'm going to get approximately 8.48. So my area under this curve here is approximately 8.48 units, whatever those units are. And we're going to go into this in more detail in 11.5b. But for now, do the problems associated with 11.5a and let me know if you have any questions. Have a great day.